For this lab, we're going to be looking at some code, and what we're really going to be looking at is based off the lab 13, but it's also kind of not based off lab 13. What we're doing is we're going to use the above results design for the 8-bit shift register. We're just incorporating a parallel load PL signal as shown in figure 4 to 7 that is included right here when PL is activated. The data in is going to be P7, P6, and so on and so forth, or just P0, that's parallel in. It's going to be loaded to the respective 8-bit register, and then it's going to be shifted as needed. We're going to use shift left, shift right. We're going to also rotate to the left, and then rotate to the right. And this is going to shift the data in the registered as desired. So we need to write a Verilog description for this. And so to do that, we're going to use our Quartus prime. So we're going to click that and then wait for it to eventually open. Now that it's open, we're going to do a new project wizard. We'll click next, and then I'm just going to save it into my drive. So I'm going to select that folder and just save it there. The name of the project, I'm just going to title it Lab 14, and then we can click next through here. We're going to create based on an empty project. We're going to go through the add files. We want to change our family to be the Cyclone 4E, and then our name filter is going to be EP4CE22F17C6. And so that's going to be this one right here. Then we can click next through this. Our simulation is going to be a ModelSim, and we want Verilog HDL selected. So we can click next and then finish the summary. From here, once this loads, we're going to want to click the little paper up here. We're going to do a new Verilog HDL file. We're going to click OK, and then we're going to have this pop up right here. So for the code that we're going to be doing, we know that we need to code the 8-bit shift register. We need parallel loads, and we need our shift left, shift right, rotate left, rotate right. So what we're going to do first is we have to make our module, right? We have to make the module first and foremost. It's titled Lab 14, and then we have to include our ports. So we know we have PL for parallel in. I'm just going to do DI for data in, and then we also have a clock that we're going to have to worry about. Then we are going to have our shift left. We are going to have our shift right. We are going to have our rotate left, and also our rotate right. Then after this, we are going to need all of our Qs. So the Qs are our outputs, and the Ps are our input loads. So we need 8 of them because we're doing an 8-bit shift register, and we always start at 0, index 0. So we're going to go from 0 to 7. It's going to look like this, but I'll just separate this with a comma and then write it on a new line and then continue it over here. So that's what that's going to look like. Now we need to label which ones are our outputs and our inputs. So inside of here, we are going to have, I'll just write it right here. We're going to write outputs, and then we want this to be a register. So since this is a register, we're going to do output reg, and then we're going to have our Qs. So we're going to have all Q0, Q1, Q2, Q3, Q4, Q5, Q6, Q7. Then we're going to want our inputs. So our inputs, we're going to write underneath this. We're going to do input. These are not the registers, so we just need to write our parallel in. We're going to have our DI. We're going to have our clock. And then we are also going to have our shifts, because those are all inputs. As well as our shifts, we are going to have our P, which is the parallel in. Those are our inputs. So we're going to have all of this right here, just like this. Now we want to run this always on the positive edge of our clock. So we're going to do always at the parenthesis positive, so just pause, edge, clock, and then we will close this off with another parenthesis. Now we can begin our code, so I'm just going to write begin, and then we can write some statements inside of here. We want to have these statements because there's multiple different things that we need to do. First, we need to load our queues. And to load our queues, we're going to load them with our p, if our p is loaded. So we can say that if, and we'll write it inside of here, if our parallel input, which is PL, is equal to 1, meaning it's high, we're going to be loading in our parallel to the queues. So in this if statement, what we're going to do is we have to have a begin, like this. And then underneath our begin, we are going to just have the P naught to the Q naught, and then the same thing for the rest of them. So it's going to look just like this. So we can see that we have a Q naught. I'm going to have it just like this for consistency. So we can see that we have a Q0, and then it's coming from the parallel input, or the parallel 0 input. And the same thing for Q1, it's coming from the parallel 1 input. And then the same thing for the rest of these. So that is what that is going to look like. And then when we're done with this, we're just going to have an end. And that is going to end that if statement. Otherwise, we're going to fall into this else if statement. And we'll deal with the first shift first. So we're going to have else if SHL is equal to 1. We're going to be inside of here. So this takes care of the shift left. So underneath here, we need our begin, of course. And then if we're going to be shifting left, that means basically everything to the right is going to be going to the left. When we start this, by the way, we're not dealing with we're not dealing with P's anymore, because we're loading them into our queues. So after these are loaded, we are just looking at our queues, not the P's. So we're going to begin. We're going to want to shift the registers from the lowest to the highest. So the highest is like 0. The lowest would be like 7. Because when we look at what we have up here, this Q7 is our lowest. Well, this Q0 is our highest. So if I were to just do like Q0, we would say Q0 has to be less than or equal to, and then we are going to have the lowest, which is our data in right here. So we're going to have it be DI. Now for the rest of these, we are going to have it look a little different. It's going to look like this. So we have our Q1 is less than or equal to the Q0. So we're going from the Q0 to the Q1. And it looks like it's going to the right, but that's just how it's written out. And we're going from the lowest to the highest. That's the left. And then the right would be the exact opposite of this. Also, when we're done with this, we're going to want to end this. And then we're going to fall into another else if statement where we do shift right is equal to 1. And so this is if we are shifting to the right. So we are going to have our begin inside of here. And then once we're inside of here, we are going to have Q0 is less than or equal to our Q1, right? Because for the right, we're going to be going from the highest to the lowest. So we're going to be going this way. So that means you can guess probably that next we are going to have Q1 right here, and going into it is going to be our Q2. And then we're going to have the same thing for our Q4, Q5, then the Q6. For our Q7, it's going to be like how we did the last one, where instead of having like Q0, we need to have our data input. So that is how that's going to look for that. And then we can just come down below it and end it. So we'll just come here and then we'll do end. Now we need to deal with our shifts. So we can come down here and say else if, and we're going to do, oh, sorry, not shifts. We just completed our shifts and we have to do the rotates. So we're going to do ROL for rotate left. And if this is equal to 1, we're going to be inside of here. And then inside of here, we're going to have our begin. And then if we're rotating to the left, just like the previous ones, we're going to be wanting to go from the lowest to the highest. So if we want to go from the lowest to the highest, we know that and this is rotating, not shifting, it's going to look something like this. Now, since it's rotating and not shifting, we are just moving these values. We're not shifting or pushing anything in, right? So we can copy all this, but what we are going to have to change is this Q0. So we can copy this, and we're going to paste it inside of here. And so we have everything except for our Q0, which we're going to handle right now. So our Q0 has to be less than equal to our Q7 because we're just rotating it, and it's rotating from back here. Now we're going to have the same exact thing for rotate right. So we're going to end this, and then we're going to come down here, and we'll do an else if, and then we're going to do ROR is equal to 1, and this is for rotate right. Now inside of here, we are again going to have our begin, and then we are going to have the same code for our rotate right. But since we are going the other way, it's going to be the exact opposite, right? We want to go, instead of when rotating leftwards, we went from the lowest to the highest. We're going to go from the kind of highest to the lower. So it just depends on how you look at it, again, like I was saying, but you can say that you're going from the lowest because this was declared after to the highest, or you could say the highest since this is higher number to the lowest. But what we're really dealing with is the rising clock edge and non-blocking assignments. So that is it for this part, and we can just end this. So we're going to end this statement right here, and then we can come down and do the end module to finish our module here. Now we can control save. lab14.v is good, so we're going to click save. Now we need to make a test bench, so we're going to go up top, click that, click OK, and now we can create our test bench code. We know the name is going to be module, and then lab14_tb, and then we have our parentheses, and then we're going to end this line. So now we need to write our inputs, and we need to write our wires, which will be the outputs. Our inputs, we know we always start with register. We are going to have our clock. There should be a space there. We are going to have our data in. We're going to have our parallel load, and then we're going to need our shifters, and then we're also going to need our cues as well. And then after this, we need to write our wires in. So this is what our input is going to look like. This first line is all the input, and this next line with our wires is all the output. So that's what we're going to have there. Now, previously we have done like a value. Whenever we write our values out, we always follow it with like a colon and then a number indicating the runtime. What we could do is make a parameter and then just reuse that as we would like a variable in other programming languages. So we're going to have parameter, and we'll just call it stimulus delay, and we'll set it equal to 10. And then we need to do our UUT. But an easier way to do this is to use DUT. For test benches, the HDL code, which is hardware design language code, is written to test another module. So that's what we're doing right here. That's what the test bench is for. The device under test is what DUT means. We can also say unit under test. So those are the two different meanings, device under test and unit under test. Previously, when we've done unit under test, we would have to do like dot, whatever we have, parentheses, and then that inside of it. If we do DUT, the only difference is that we don't need to have any of that, and we can just separate them with commas. So it's going to look something like this. We're going to have our name still, lab14, we're going to have DUT in uppercase, and then we're going to have our different values. So this is just from earlier. We're going to have PL, we're going to have DI for parallel load and data in, and then the rest should be the same, where we have the clock, the shift registers, and then our Qs, and then the Ps as well. Now there's a couple different scenarios that we're going to want to model. It's actually multiple different scenarios. First, we are going to have just loading our values. So when the clock is 0, we're going to say that our parallel load is 1, the data in is 0 at this time, and of course all shifts are 0. Now we want to load our values because the parallel load is 1, so values should be 1. Now, knowing all this, remember, clock is 0, parallel load is 1, data in is 0, shifts are 0, values are 1. We can come down below it, and down below, we need to have our time. So just like previously, we're going to do the pound. We are going to have inside of parentheses the stimulus, and I am just going to do an underscore, and then switch that out. That way, it's a little bit easier to see. So we have stimulus delay, and then after this is where we actually write out the code. So we're going to set our clock, and we're going to initialize it to 0. Oh, also before this even starts, we're going to want to set our clock and our data in to 0. So we can come up to our registers and set this to 0, and then we're also going to set this to 0. So those are both 0. Our clock is 0 here. Our parallel input is going to be 1, so we're going to do PL is equal to 1, and then we know our data input is equal to 0, and then our shift registers are all 0. Now that we have that, we can also set the P values to 1, so we're just going to have it look like this, and then well, we can kind of see it like this. Yeah, so it looks good like this. We have stimulus delay, we have the clock, our shift registers, and then the parallel values are all 1. Values should be 1 because we need to load to our queues. And this is just for the test bench. We actually do that inside of here. That's what we coded out in this first if, not that first if statement. In this first if statement, if the parallel load is 1, we're going to have all of these values be 1, and then they're going to load in to these right there. So that's how that would work. And then we would come down here, and all we're going to do this next one, I'm going to copy it because it's basically going to be the exact same thing. Now we just want to say when our clock is 1. So clock is 1 here, and then everything else is just going to stay the same. So that's the code for that entire first part. Now we can move on to the next. And so the next one is when we are actually setting all of our values to 0. And we want to do that to test everything, just to make sure if we were to set our parallel values, our loads to 0, everything would be 0. So I'm going to copy this. We can paste this down here. The clock's the same thing. The parallel load is still 1. So I think I might have said that we are changing it so we don't have a load here. But no, we will have a load here. The data in is still going to be 0, right? Our shifts are still 0, but the parallel values are 1. So the reason why our parallel load is 1 is because our load has to be high, otherwise we don't have a load. It's either 1 or 0, yes or no. So 1 meaning that we do have a load, just the values are 0. So if we do that, all of the values inside of here, instead of being 1s, will become 0s. Now from here is where we need to test our rotations. We've tested our loading with the 1s and the 0s, and now we are testing the shifting and the rotation of our bits. So we're going to do a before rotation just to lay everything out. So we're going to say before rotation, and we know this is an 8-bit register, so we should have 8 bits, right? So our value is going to be like 1, 2, well, that's very close. 1, 2, 3, 4, 5, 6, 7, 8. So we're going to have 8 numbers here. Now what I want to do is I want to test everything and lay our 1s in the middle. So we're going to have 0, 0, 1, 1, 1, 1, 0, 0. So those are the 8 bits that I'm going to be working with, but you can put them in any order you want. It doesn't really matter. It's just I like things in the middle. So my OCD would kill me if I didn't do that exactly. Now we have to say that same thing where we first did the clock is 0 and then the clock is 1. So first we're going to say that the clock is 0, the parallel input is 1, our shifts are 0, shifts and rotates are 0. And also, most importantly, we need to initialize our values, because these values, what we have right here, they're being tested inside of this code, right? This code doesn't call upon any values. It just does things. This is actually testing it with values. So this is very important. We need to initialize the values in whatever order we specifically choose it to be in. So just like previously, we are going to have to write for the stimulus delay. So we are going to come in here and we're going to do the pound parenthesis stimulus underscore delay. And then after this, we're going to test when our clock is 0 and then when our clock is 1. So first, clock is equal to 0. Next, we have our parallel. So our parallel load is going to be 1, of course, because we are testing it when we have a load. Our data in is still going to be 0. I don't think I wrote that out up here, but our DI will be equal to 0 again. And now is where we write our shifts. Well, our shifts are also going to be 0, just like this. So I'm going to copy and paste this down here. Now we need to initialize our values. And so when we initialize our values, we can obviously see if we look up here that P0 and P1 are going to be zeros. The middle is going to be ones, and then the last two are going to be zeros. So I've written this out before, it's in my notes, but it's basically very simple, and we are just assigning these values. So this should be a P0 is equal to 0, and then we have P1 is equal to 0 as well, and then like I said, just for the rest of them. So that is the code there. And then we are just going to copy this because it's the same thing. The only difference now is that we want it when our clock is 1. So I'll come down here and then I'm going to say, well, when our clock is 1, we want all of this to happen as well. Now is where we need to test our rotations. So we've done all this, right? So this was, I'll title this loading test, and this is before rotation. I guess this should be capitalized. So we have before rotation here, loading test, and then after this is where we need to test our shifts and rotations. So this is, this is before shifts and rotations. So we're going to test our shifts and our rotations inside of here. First thing that we're going to deal with is a left shift. So for the left shift, our output should be the following. We want to shift, if we look at what we have right here, if we look at what we initialized, we want to shift everything to the left, to the highest part. So this is going to be shifted to be a 1, and this is going to be shifted to be a 0. We're going to have the same stimulus delay. Our clock is going to be 0. Our parallel input is going to be 0. Our data in is also 0. So what we're going to have here is, of course, our stimulus delay. And we're always going to have this. And then we are going to try setting our clock equal to 0. We want our parallel load equal to 0 because we are rotating. We're not loading anything, right? We have everything loaded already. That's the assumption. Our data in is also going to be 0. And now we are going to have to label all of our shift registers as 0 and our rotate as 0. So this should be 0 as well. The only thing that we should have that's being shifted is this right here. So we're going to shift to the left. We have shift left 1. And this is when our clock is 0 and all that stuff. Now we're going to want to copy this and we can paste it down here. And we're going to do it when our clock is 1. So this is all that we need right here to get it to work. And this is for our left shift, right? Now, what if we have a right shift? So we will say for our right shift output, what should it be? Well, if we're shifting to the right, we're going to shift this 0 over, and then we're going to shift this 1 over. So it should look like the original input. That means for our clocks, we're going to have the 0, 1. Our shift left should be set to 0. And now our shift right should be 1 for both of these. Now, we're going to want to deal with the rotations next. So we have the left rotation, the rotate high, and then we have the rotate low bottom rotation. It's going to be very similar to this, so I can just copy and paste it. That way we don't have to code it out again. I'll just label this as left rotation. Now, what should we have if we have it set to look like this? Well, our left rotation, what we're going to have here is we want to rotate to the left. This is going to be a 1, and this is going to be a 0. Now, actually, I might have made a mistake. I did make a mistake, and it was in the shifting. Because if we shift, if we have our 1, we're going to be shifting our data in. And our data in is going to be 0, right? So really, what we're doing when we set the data into 0 is we're shifting in a 0 for the Q0. But I mean, since we're not really touching it, it doesn't affect it, I don't think. We'll find that out in the waveform simulation, but that's important to note. There is a difference between these two, even though they look the same. There's a difference between the rotation and the shifting, and that's because in the shifting, you're going to be shifting this in. And then when you're shifting right, you're going to be shifting this in as well. So that's how that would actually differ from this. And so for the rotate, now getting back on topic, we have it look like this. This is just going to be a 0. This is going to be a 0. Our rotate left is 1. Rotate left is 1. Now we're going to do the same thing before the right rotation. So with the right rotation, obviously we're just going to be rotating to the right. We're going to have a 0 and then a 1 here. Now if our 1s right here were like more to the end, like they were right here, and we did our shift, I'm harping on this again because it's important, because there is a difference between the shifting and the rotation. We would be shifting in a 0, like if we had 1s here, right, and we shifted it to the left, we can see that we would load our Q0 with DI, and DI is 0 right here. So we wouldn't be shifting this way, right? We would just be shifting a 0 in. That's what we're shifting in. And that'll make more sense when we do the waveform. But after this, what we're going to want to do is end, and then we'll have an end module. Now we can compile this. We're going to click yes to save this. We want to save the Verilog 2 because I've saved the lab 14. Now we need to actually save the test bench, which is Verilog 2. We're going to save this as lab 14, and we'll do .tb. Now it seems that we have some errors and some warnings, and it looks like it doesn't like something with my syntax, and I am missing a semicolon here. And let's see. Oh, so we have a single end right here, but this is just to end the statement right here. We also need an end to end our entire thing because we have a beginning right here. Whenever we have a begin, we need an end. So I'm just going to write end here, and then I'm going to recompile it after I click yes to saving it. So that should not be a .tb, it should be _tb. Oh, it says di is equal to 0. You know what that might be? It's because we declared it up here. So instead of declaring it up here, let's try taking this out, and we'll declare it underneath our, and actually I think I know what's wrong, is that we need to close this because I never did an initial begin. So I had my parameter, right? I did my DUT, and then I just went straight into coding. I think I have an end and an end module, but I never have a begin. So that's important. You want to have a begin. You always need a beginning, and we're going to do an initial begin like this. So we'll set clock equal to 0, and then our DI equal to 0. Make sure you want to end these lines as well. I can't spell initial. It's N-I-I-T-I-A-L. I think. I hope. It seems that we are missing this in line 27. We're missing a semicolon, and I can see it's right here. We have a little comma instead of a semicolon, and since I copied that, it might also affect this as well. see if it affected anything else. Looks like those are the only things that are affected, so we can try compiling it again and see if it runs. And we have no errors, so that's great. I'm really happy. We're gonna go to Tools, Run Simulation Tool, RTL Simulation, let's go! And the feather will pop up. It'll pop up. It's gonna pop up right now. So we're gonna click that little feather. I did kind of mess up the format of this, but don't mind that. As long as we have our waveform, and if you don't have the waveform, you click View, and then you select Wave down here. So let's go up to Compile. We'll click Compile. Let's find our things, and they are indeed here. We're going to compile both of these. Compile. Since mine are over here, I should check to see if there's any errors. There are no errors so far, so that looks good. We're going to go up to Simulate, Start Simulation. We want to expand our work, click our test bench, click OK, and then we are going to click in all of these values. Also, I'm not 100% sure if changing where we assigned the clock and we also don't need to click our parameter. We can see up top I have the stimulus delay. That's the parameter. We don't exactly need that. But remember when I changed the values under initial begin, where I assigned them down here? I don't know if that's necessarily true anymore because we had other errors that we had to fix. We can come back and test that, but we might be able to just assign them up here. But that is yet to be proven. So I've clicked everything, I've loaded everything into here. I'm gonna just change the run length to 200 picoseconds. And right now it's in nanoseconds. And then we can click run. And this is our waveform. So I will zoom full. Now, we have a few things that we can look at when the clock is 0. This is what we are going to have. When our clock is 0, but we have one parallel load input, we can see that our parallel loads are all 1, right? And then when our clock cycles to 1, we can see that at the bottom, the cues are going to be loaded, okay? Now we go to the next thing, and we can see that once our clock is off, right? And we're gonna go, everything is 0. All of the parallel inputs are 0. When the clock goes on, this is basically resetting it, right? We're loading our values here. The clock goes on, activates everything. Our cues are going to be 0 to represent that. Now we should, right here, we load in the values to our P, right? That's when the clock is off. When the clock is on, our cue values are loaded in. Now is where we get into our shifting and our rotating. So clock is off, we can see that shift left is highlighted. So we should be shifting left, right? And remember, we assigned everything in here like this. So when the clock goes on, we can see that we have shifted to the left. We are shifting down. Well, it's down how we're looking at it right now, but we can also say it's up. It's depending on how you're looking at it, it's shifting that way. But after we do this, it's shifting towards the lowest bit. After we do this, now we can see that the clock is off. We want to shift right now. Now it should shift us in the other direction and put us back to where we were. So it doesn't do that. We have 1, 1, 1, and then we have a 0 here. And I believe that is because of our shifting. Remember when we shift right, we have DI for Q7. So in DI is 0, so that's probably why the 0 isn't right there where it is. But let's see if we do rotates. So if we want to rotate, we can see that we have 3 in here, right? Because the other values shifted in here. We're going to be rotating down. We can see everything rotates 1 down, and then if we rotate up, everything should rotate up. I believe that is correct. So let's look at our test bench again. Something doesn't look right with the rotate right, because we can see that we just rotate right again. So I'm going to look at the test bench again, and we can see that our rotate left here, I never changed it. So what I'm going to do is I'm going to change the right rotation to be 1s. And what I'm going to do actually is cut the rotations and then put them on top of our shifts. That way we can see the rotation before we see any shifting of 0s into our values, because we are going to be shifting some 0s in. And then I made the rotate left 0. So let's compile this again. We're going to click yes because we want to save it. Okay, now that's loaded. We're going to go to Tools, Run Simulation Tool because we can do that now. We're going to go to RTL Simulation, and we can see that the little feather should pop up. Our boy pops up. All right, so we're going to full screen this. We're going to click View up at the top. My whole screen isn't showing, but that's just because of macOS not being great. We're going to click Wave, and now we need to click Compile again up top. Go to the directory where it is. We need to compile. I like to compile both files, just to be safe. It's always good to be safe. Click somewhere, click Start Simulation, expand work, click Test Bench, click OK, and I'm going to drag all this down. All right, now hopefully it'll work. If not, no, it will work. It will work. I have faith in in everything right now. So we're gonna place this here. We want this to be 200 again, just as previously, and click Run. We have clicked Run. It has run. We're gonna zoom full, and now let's analyze this properly. So when everything still stands as we've done previously, we're just going to be looking at the actual rotations and stuff now. So when do we start rotating? We start rotating left here. So before here, we have all of our things. All the things are here. We have our values loaded here. Now here's where we start rotating. So everything should rotate higher. So if we move it over here, we can see that everything moves downwards. And it's only downwards with respect to how we're looking at it. Now everything should move back up to its original position, and it does. We have rotated right. We can see that it has moved back up. I'm just going to go through this really fast. We have this initial position, we rotate down to the left, and then we rotate back up to the right. Now we're going to deal with shifting. So let's see, we can see our shift left has lit up, or it's high. And now we can see that we are going to shift a 0 in. So we can see that we shift a 0 in. Well, technically we're not shifting a 0 in here. We're shifting our 1s down. But we're going to shift a 0 in when we go here. We can see we shift a 0 in when we shift to the right. And that's it for this lab. That's it for this code. It works. If you have any questions, you can leave them in the comments below. If you like the video, what would be nice if you hit the